I'm Syed Ali Turab. I will be talking about the escarpment evolution of the Red Sea margin of southwestern Saudi Arabia, insights from low temperature appetite thermochronology. I would like to acknowledge my colleagues from Austria, from Scotland, Ireland, and France who remain part of this work. To begin with, I would like to talk about the escarpment evolution models. Mainly, there are three models put forward for escarpment evolution following a continental breakup. They are down-wearing, down-warped, and escarpment retreat. This figure shows a block diagram of these three models, where the thick line shows the present-day topography of the escarpment, and each of these models have different characteristics with respect to their erosional history. For example, denudation in the downward model is almost negligible or zero near to the coast, and it increases to a maximum at the base of the current day escarpment. Similarly, in the scarp retreat model, erosion is intense at the base of the escarpment throughout the history of its evolution. Whereas in the down-wearing model, here, the area seaward of the escarpment observes almost the same denudation rates. Okay. There are predictions put forward for all these three models using the appetite fission track ages and the appetite helium ages. Here in this figure, figure B, you can see that the downward model predicts the distribution of appetite fission track ages across the coastal region, and the ages are almost similar to those of the ages observed on the inland plateau, and they are much older than the age of the rifting, whereas the ages predicted by the scarp retreat and down-wearing models, they are almost same as age of rifting, and in some cases they can be younger than the rifting age. Similarly, figure C shows predictions of the appetite helium ages for the down-wearing and the scarp retreat models. The key here is the location of the youngest ages, or the samples giving the youngest ages in the scarp retreat model. The ages show a gradual trend of decrease in ages or younging in ages from coast towards the base of the present-day escarpment, whereas in the down-wearing model, the youngest ages are found halfway between the escarpment and the coast. Okay, this is the figure which shows the location of study area. That is the escarpment of the southwestern Saudi Arabia and its coastal plain in relation to the Red Sea rifting. The Arabian continental block, or the Arabian plate, this was detached at around 25 million years from the northeastern Africa. The Afar mantle plume down here played a key role in the location of the rift, and the direction of the rifting was controlled by the subduction zone in the northern New Tethys beneath the current Bitlis-Zagros thrust zone. The direction of extension changed at around 14 million years from rift normal to highly oblique to the rifting direction, and parallel to this Kaaba-Levant transform fault. This timing corresponds to the collision of Arabia with Eurasia and the creation of transform boundary cutting through Sinai and the Levant continental margin, linking the northern Red Sea to the Bitlis-Zagros convergence zone. It also roughly corresponds to the creation of the oceanic crust in the Red Sea, roughly at 13 million years, which was previously believed to be starting at 5 million years, but recent studies have indicated that the oceanic crust started to develop in the Red Sea at around 13 million years. So Okay. Okay, so this figure shows the SWOT profiles constructed along the Saudi Arabian escarpment region. You can see that the Saudi Arabian escarpment shows spectacular morphological characteristics that are more prominent than those of the well-known southeastern escarpment of the Australia and the Drakensberg escarpment of South Africa. The Saudi Arabian escarpment is about 3,000-meter high, which includes the highest peak of the Saudi Arabia, Mount Al Suda, and also further south, the highest peak of the Yemen, which is the Jabal Nabi Shuaib, which has the elevation of 3,650 meters. It shows a vertical drop of 1,500 meters in less than 5-kilometer distance. And morphology of this escarpment remains uniform for about 1,000 kilometers, separating rugged topography towards the coastal side below from the inland high elevation plateau. Okay, methods used are the appetite low temperature thermochronology. Thanks to Sam, he had already covered this part. So I'll not go into the details here. And second part is the geomorphic analysis. And in geomorphic analysis, we used curved SWOT profiles, which I've already shown in the previous slide, and the stream power analysis. For the stream power analysis, we study channel characteristics in comparison to the geomorphic steady state, where channel slope S and drainage area A are related by a power law function. S is equal to Ks into A power minus theta, where Ks and theta are the steepness and concavity indices respectively. We have calculated the normalized steepness index KSN for a fixed reference concavity value, theta reference. The parameter KSN can be used as proxy for erosion rate. So the variations in steepness index can thus be used to infer zones of geomorphic disequilibrium and ultimately variable exhumation rates. This is the map of the study area showing the distribution of the different rock types and the location of the samples collected. The red shows the Cenozoic volcanic rocks. The yellow is the Cenozoic surficial deposits. The green is the Mesozoic and Paleozoic sedimentary rocks. And the area that is not being colored or which shows the hillshade in the background shows the rocks belonging to the Arabian-Nubian shield. A noteworthy thing in this map is the single outcrop of Nubian sandstone, which was observed or found in the field near the location of the Mount Al Suda, which is the highest peak of Saudi Arabia. So this is only a few square kilometers in size, single outcrop, and this places tight constraint on the exhumation related to the escarpment evolution. Okay, some field photographs. Okay, here in this one, near vertical drop from the top of the escarpment, the two arrows shows two persons standing here for scale. In B, the Nubian sandstone outcrop at Mount Al Suda, and you can see the view towards the inland plateau. And D is the Google Earth view of the escarpment region and the inland plateau. Okay, some more photographs showing the panoramic views from the top of the escarpment towards the coastal region, showing the sharp interflows indicative of the intense erosion. Okay, stream power analysis was carried out across the study area. And these streams are color-coded according to the KSN values. The escarpment is shown by blue color and the drainage divide is shown by white color as shown in this inset. The escarpment forms the drainage divide for majority of its length in the study area, with few exceptions as shown in the inset with these white arrows, you can see. Looking at this SWOT profile east of the escarpment, this area towards the inland, the mean topography exhibits a smooth concave shape, typical of flexural rebound inland of a retreating escarpment. West of the escarpment, the mean topography is also strongly concave. Interestingly, the KSN of the west draining channels often has maximum values in their central part, as shown by these pink arrows. The absence of flexural bulge is interpreted in terms of significant erosion. You can see there is no flexural bulge visible on this SWOT profile here. So we interpret this as to be showing dense erosion, and which is keeping pace with the bulge of this part. And then overall, these morphological observations support that the second stage of the rift flank evolved by escarpment retreat. So this is based on these geomorphic analysis. Now we come to the thermochronologic data. This shows the distribution of the apatite fission track and apatite helium ages across the study area. Here on this map, I have also shown the apatite fission track ages of Bohannon et al. That are younger than the 32 million year, which we use as the cutoff for the processes related to the Red Sea rifting. So these gray boxes, these are ages from the Bohannon et al., and all the other ages are from this study.
So yet you're at 11 minutes now.
Okay. Okay, apatite fission track ages plotted against elevation. They show good enough correlation. And here we interpret bottom of the exhumed partial annealing zone to be lying at a current 200-meter elevation, with the exception of these two samples, which we interpret as to be belonging from the down-thrown blocks along the normal faults from the southern parts of our study area. And this faulting is also reported in the literature by Bohannon et al. Okay, and there was no correlation observed in the single grain apatite helium ages and the effective uranium content, as well as the grain diameter. Apatite fission track ages range from 352 to 13 million years. Okay, I'll skip this. Okay, average apatite helium ages range from 220 million years to 2.9 million years. We were only able to get track lengths from 4 samples. If you can see here, samples 31 and 34 from the top of the escarpment, having elevation more than 2200 meters and ages of 352 and 330 million years, they show similar mean track lengths, showing that they were most probably residing well above the partial annealing zone of the apatite fission track system. Whereas the samples 37 and sample 46 with apatite fission track age of 72 and 120 respectively, and elevations of 1600 meter and 875 meter respectively, they were most probably residing in the partial annealing zone. This is shown by the lower values of mean track length for sample 37 and the bimodal distribution of the track lengths for the sample 46, with the older tracks observing track shortening and track annealing, and the younger tracks showing the longer lengths. Okay, total amount of rock and surface uplift. This is not only constrained by the chronological data, but also by the presence of Mesozoic sediment outcrops on the top of the escarpment, and that sediments were believed to be like they were 500 to 1000 meter in thickness, and since they were formed near the sea level, so this would mean that the uplift in the range of 35 to 4000 meter had taken place after the rifting, and these values are in agreement with the values reported by other workers. Similarly, Bohannon et al. From the same area reported 4 kilometers of rock uplift, and out of which 2.5 kilometers had occurred since 13 million years. 13.8, which was the age of their youngest sample. So our data also support this estimate. So overall, the exhumation is about 4 kilometers. Okay, now we come to the predictions for the three models: hepatite fission track age distribution or age predictions across the escarpment and coastal regions. So this figure shows our hepatite fission track ages. Clearly, we can see that the ages along the coastal region, they are younger than the ages in the inland plateau or the escarpment region. And even some samples are having ages younger than the rifting age, which is marked by this dashed red line. So with this pattern, we can confidently reject the downward model for the evolution of the escarpment in the southwestern Saudi Arabia. Since the difference between the predictions for the scarp retreat and downwearing model in AFT ages is not large, so we cannot use AFT age for distinction between these two models. So we take help from the hepatite helium data. As I already mentioned, that the key here is the location of the youngest samples. So when we plot our data here in this figure, the red points, the red square, they are the hepatite helium data. So the location of these two samples, they are showing the youngest hepatite helium ages. This is roughly halfway between the coast and the escarpment. Thus, it supports the downwearing model of scarp retreat. While downwearing model is consistent with the age data, it is somewhat inconsistent with the morphological shape of the escarpment. The concave upward shape, as I already mentioned in the beginning, of the inland side of the escarpment and the coincidence of the escarpment edge with the water divide indicate flexural rebound process that occur in response to massive asymmetric erosion on the coastal side and scarp retreat processes. We suggest that this conflict may be resolved by invoking a two-phase evolution of the escarpment that is supported by the geomorphological observations as well as the thermoclinological data. Indeed, a two-phase escarpment evolution model can explain the large age difference between the FT ages and the AHE ages, which are like the fission track ages are Miocene and the hepatite helium ages are Pliocene. Otherwise, without this, this would mean unlikely dramatic decrease in the cooling and probably exhumation rate between the closure temperatures of both systems. Okay, so this diagram shows the...
Syed, we're at 18 minutes now. It's time to wrap up.
Okay, so I'll just explain this figure and then I'm finished. This is the last one. Okay, this figure shows the two-stage history. Here you can see the first stage involves the time period prior to the formation of the ocean lithosphere. Here, the updoming occurs in the western Saudi Arabia, and west of it, we have the decompression melting and thermal weakening and volcanism taking place. And around 25 million years, the breakup of the plate happens here, somewhat west of the maximum thinning, and followed by the erosion of the up dome area and the rift flanks on the both sides of the Red Sea rifting. So this stage involves the, according to our estimates, 1 to 1.5 kilometers of exhumation. Second stage commenced with the onset of the formation of oceanic lithosphere. So this oceanic lithosphere brought the downwarping of this part and consequential uplifting of the already uplifted escarpment region. So in the end, the last step, the favorable orientation relative to the trade wind now started to cause substantial orographic precipitation, the resulting massive. So this is due to the last erosion is due to the massive post-13 million year erosion on the west side of the divide formed a distinct escarpment and ultimately a second phase of cooling due to the exhumation in the Pliocene. Okay, I think I've already to these things. This is published in the EPSL, and related work is also published in Nature Communications. Thank you.